Scientists once believed that every single problem in physics could be solved using classical mechanics, Newton's laws of motion, or some derivation thereof. When we apply a force, that will move an object forward. These are the kinds of assumptions that we're looking at, these basic notions that we have when we look at the classical world. But beginning in the late 1800s, scientists began to realize that classical physics couldn't answer our questions about very small subatomic particles like electrons. In the 1920s, a few trailblazing scientists pioneered a new theoretical language for thinking about the subatomic world called quantum mechanics. In classical mechanics, again, you can simply predict the position and momentum of an object based on the amount of force applied to it in any direction. It's very easy. You can do this using pretty basic math. For example, if I apply 1 Newton of force to an object that weighs 1 kilogram, it will accelerate 1 meter per second that I apply that force. And thus, after 1 second, its momentum is 1 kilogram times 1 meter per second. So this is pretty easy. Corresponding to how much I push it, it goes a certain momentum. And this is, you can calculate this basically using arithmetic. However, in quantum mechanics, if you know the position of an object, all that you can find out is a range of possible momentums. And if you know the momentum of an object, all one can find out is a range of probable positions. So we're left in this spot where the more we know about an object's momentum, the less we know about its position. And the more we know about its position, the less we know about its momentum, as opposed to the classical world where we can know both its position and momentum at the same time. So that means that when you transfer energy to objects on the atomic or subatomic scale, they don't move in predictable ways, but they have pretty great uncertainty with respect to either their position or momentum, or both. So in 1894, Max Planck solved the problem of black body radiation. And what this problem was is like, you put things in a furnace and it turns red hot. That's a common expression, red hot. But why does it turn red? According to all the prevailing theories in the 19th century, when a perfect metal is heated up to thousands of degrees, it should emit blue light because that's the spectrum that that metal emits at. And yet we've observed for many centuries, if you put something in a kiln, that when you put metal into furnaces, the hot object emits red light. So thus our explanation for black body radiation of red light was out of whack with the observed facts for many decades, but no scientist could rectify this explanatory discrepancy until Planck came around. So why do hot objects glow red? For instance, iron turns cherry red around 1300 degrees Celsius. It's very hot, but it turns red as opposed to emitting blue light. And the physicists thought that metals should glow blue at this temperature because they were still thinking of light as a classical force called electromagnetism that is continuous on all scales, meaning that it can come in whatever size or packet you want it to. It doesn't have to come in discrete chunks. And now we know that light is caused by moving electrons, and electrons are a unit of things. You can take one electron, and that has a definite meaning. You can't have half an electron. That doesn't make sense. So there is a scale where you have to have 1 or 2 or 3, but you can't have 1.78. That doesn't make sense. So we know that the light is caused by moving electrons, which come in discrete packets of energy. It's like the difference between how much sand and how many rocks can fit in the container. A sand fitting in the container, it's almost continuous. You can almost fill the entire container. Whereas if you have rocks, depending on how big they are, it could only be 30% of the container is actually full and the rest is empty space. Although they're superficially similar substances, sand and rocks, the continuous sand will fill the entire container, whereas the discrete rocks will not. And discrete means that it has to come in these packets and can't be and you can't have a fractional amount. You have to have an integer whole number of these packets. So similarly, suppose we treat electrons as continuous rather than discrete units. That will lead to problems. In that case, we'll predict that black bodies should grow bright blue at all temperatures, as scientists did for a quarter century. Although this problem may seem trivial, it is not. According to classical physics, all objects should glow in the dark. There should be no darkness. Although this is obviously untrue, scientists spent the last 25 years banging their head against the wall trying to figure out why. But then at the turn of the 20th century, in exactly 1900, Max Planck discovered the solution to the famed black body problem. Instead of treating electromagnetic radiation as a continuous force, he quantized energy, meaning that he restricted the number of possible values of the distribution of energy so that certain variables can assume only certain discrete magnitudes. So that means it has to come again. One magnitude, two magnitudes, 3 units, 4 units, 5 units, but it can't be 2.5 units. It can't be 6.8 units. That it has to be it has to assume certain discrete magnitudes. So therefore, matter particles cannot vibrate in any way they please, but only in frequency that abide by the rules E equals NHV, where N is any integer, V is the frequency of the particle's vibration, and H is a constant to be chosen by Planck. Thus, energy can only come in whole number multiples of the energy coin HV, which is Planck's constant multiplied by the frequency of the object. Any other unit is not recognizable to the system. It doesn't have a meaningful amount. So energy can only come in whole number multiples of the energy coin HV. You can have 1 HV, 2 HV, 3 HV, but never 1.5 or 2.7 HV. The energy coin HV is just like a penny. If you have 1, you have 1 cent. If you have 2, you have 2 cents. If you have 3, you have 3 cents. But if you break a penny in half, it is no longer even on the scale of value, right? So you can't have half of an energy coin. You have to have a discrete number of them. So originally, Planck wanted to lower Planck's constant to 0 so that energy particles could have any energy value they like. This is the obvious solution to how we should think about things, that things may be discrete on a certain level, but ultimately they have to be continuous. And what Planck discovered is that actually reality is not continuous at that level. It comes in these discrete packets of energy coins of HV. So just like in classical physics, what we'd expect is that objects can be 1.789 meters or 2.6 kilometers or 9.8 millimeters, and all of these are intelligible values. Object trajectories are not usually treated as discrete, but they're actually continuous at the classical scale. They move through all intermediate values of position and momenta when they change velocity or change position. They don't. There's no jumps or breaks or it doesn't have to leap out of the manifold in order to travel to a new point. So, however, at the quantum scale, this same kind of continuity does not hold true at all. Nick Herbert says Planck's assumption was not justified by any physical reasoning, but was merely a trick to make the math easier to handle. Later in his calculations, Planck planned to remove this restriction by letting the constant h go to 0. This would make the value of the energy coin so small that the particle could have effectively any energy it pleased again. So this is the solution. He introduces this constant, which is meant to make the math easier, but eventually he'll get rid of this by making it go very infinitely close to 0, just like we do in limits with calculus. However, Planck found that when he let h go to 0, his equations predicted the same blue body glow as all other scientists. However, when he set h to a very low but non-zero constant, which it's around 10 to the negative 34, his calculations perfectly matched the experimental results of red black body radiation. It was only when he treated energy as discrete rather than continuous that he was able to predict the red glow of hot metals, proving to the world that energy could only be counted in discrete packets. Using the experimentally discovered value h, which fits the data, we now call that Planck's constant, which is 6.6 times 10 to the negative 34 joules per hertz, in terms of which all units of energy are quantized. You can only have units in terms of Planck's constant as a multiple of that times the frequency. So again, in a given system, a particle's energy cannot take any value but must come in whole number multiples of hf. Planck's constants multiplied by the frequency of the radiation. This is how an incandescent light bulb works. Before it is turned on, it has a temperature of around 20 degrees Celsius, which is low enough that it's not going to be emitting white light. But when it's turned on, it has a temperature of around 2000 degrees Celsius, causing the filament to generate nearly white light as it glows at this very high temperature. So if the light bulb were less bright, it would glow cherry red. And if you followed the assumptions of classical physics, your light bulb would be blue at all temperatures. There would be no point in turning it on because it would always just be the kind of incandescent blue. So the next thing that we really need to talk about with respect to the basic foundations of quantum mechanics is, one, they're different from classical mechanics. Two, energy is quantized in this system, meaning that it is discrete. It is not a continuous system like classical mechanics. And three, the quantum objects are not just particles, they're also waves. And it is in the coincidence of these two aspects, the duality between wave and particle, that we define the mechanics of the quantum world. So since we discretely quantized electromagnetic radiation into packets of 0 HV, 1 HV, 2 HV, etc., we can think of each HV, each unit of energy, as consisting of 0, 1, or 2 particles in the same way, each with an energy HV. So what is one particle with the energy HV? These particles of electromagnetic radiation are called, what you may have heard of this, it's called a photon. And these are the particle character of quantum objects. An individual photon has an incredibly small energy value, but not zero, because it is discretely quantized. So there is a unit of light, then there is an amount of these photons, there's an amount of these light particles that can lead to these large-scale effects. For example, a 100-watt yellow light bulb emits 2.8 times 10 to the negative, 2.8 times 10 to the 20 photons in 1 second. So that's a lot, but it's not infinite. So there is an amount of photons that you can get to form light, to form what we perceive as light. But wait, you might ask, isn't light a wave? Isn't this contradictory? This has been known for hundreds of years. We had previously considered light to be a particle way in the distant past, but hasn't this gone into the dustbin of discarded scientific theories along with bloodletting and flat Earth? Well, yes and no. The amplitude of a wave is the distance from its highest point to its midpoint. A 10-foot tall wave has an amplitude of 5 feet. Waves add their amplitudes. If two 10-foot tall waves combine in sync, the resulting wave has an amplitude of 10 feet and a maximum height of 20 feet. However, if the waves are out of sync, i.e., if at the point they meet, one of them is at the lowest point and the other is at the highest point, and they have the same amplitude, then those two are going to cancel each other out. The negative value will be the same as the positive value. So when you add them together, you get to zero. And the waves cancel each other in a process called destructive interference. Obviously, waves are unlikely to meet at their exact minimum or maximum points. So when two waves combine, they usually exhibit interference somewhere in between the maximum and minimum possible values. For example, if two waves meet when one of its peaks is at 10 feet and the other is at 7 feet out of its 10-foot maximum, the new amplitude of the wave will reach a modest 12 feet. This is called constructive interference. Since the second wave is 2 feet above where it started, the peak of the next wave, where you have these two combined waves, will be 10 plus 2 is 12 feet in amplitude. So we consider light to be both a wave and a particle. The reason why we know that it's a wave is because when two paths of light combined as they pass through a crystal, they either exhibit constructive or destructive interference. So we know that they're actually, unlike objects can't do this, they don't combine in the same way, combine their amplitudes. Obviously, amplitudes are only a property of the wave character of quantum objects. So we've done these experiments, we've shined light on crystals, on metal, etc., and they actually interfere with one another. There is a wave pattern that is displayed on a screen, and there is constructive and destructive interference, and we can see the patterns wherein the light waves are interfering with one another. So we know that light is a wave. As Peter Atkins says in his classic textbook, Physical Chemistry, we've also seen that waves of electromagnetic radiation have particle-like properties. Thus, we are brought to the heart of modern physics. When examined on an atomic scale, the classical concepts of particle and wave melt together. Particles taking on the characteristics of waves, and waves are characteristics of particles. So we can't treat light as either a wave or a particle. We have to treat it as both, as there being this intrinsic duality between these two aspects, wherein light is both a wave and a particle, and these are two phases of the same object's existence. So, in fact, every physical object has both a wave and a particle character. However, objects with much greater mass than quantum objects have such undetectably small wavelengths that their wave-like properties cannot be observed. The joint particle and wave character, Atkins says, of matter and radiation is called wave-particle duality. The total failure of classical physics for small objects implies that its basic concepts are false. A new mechanics had to be devised to take its place. So this is what we're talking about when we're talking about quantum mechanics. We're talking about something which is different from classical mechanics. We're talking about treating quantum objects as both waves and particles and treating them as discrete units. So that means that we have to have some sort of explanation for how waves become particles, some sort of function that would mediate between this potentiality wherein there is a space of potential particles that can be generated by that wave function and the actual particle character of the quantum object, which is then actualized. So the quantum mechanics is all about the relationship between potentiality and actuality, which are represented respectively by the wave and particle character of quantum objects. So that is basically what we're talking about with the basic principles of quantum mechanics, is that it's all about the difference and the intrinsic connection between the wave and particle character of quantum objects. So thank you. Take care. God bless.